All right, so we're going to get started. I don't know if you've ever seen this. This is one of my favorite places to start with electrical diagnosis. It's probably hard to read this on your screen, but there's a quote in here. This is page 48, and this is an old school electrical diagnostic guide. It's I forget the title of it, but this is from the, I believe this version is from the 1930s, but I'll read it to you. It says, electricians often test circuits for the presence of voltage by touching the conductors with the fingers. This method is safe where the voltage does not exceed 250 and is often very convenient for locating a blown out fuse or ascertaining whether or not a circuit is alive. This is my favorite line. Some men can endure the electric shock that results without discomfort, whereas others cannot. They're definitely man shaming you. If you can't grab 250 volts and use it for electrical diagnosis, 1930s man is looking down on you right now. And then it goes on. If you go to the next page and stuff, it actually talks about checking low voltages by placing the wires in your mouth. And I think it says the present. Let's see this. Yeah, there it is. Actually, if you look down at the bottom, it says the presence of low voltages can be determined by tasting. This method is feasible only when the pressure is but a few volts and hence is used only in bell and signal work. Where the voltage is very low, the bared ends of the conductors constituting the two sides of the circuit are held a short distance apart on the tongue. If voltage is present, a peculiar, mildly burning sensation results. Anyway, they literally used to teach this, and there's no huge technical benefit to this other than just to point out that long ago, people were maybe much dumber, but also much less risk averse than we are today. And I'm not going to pass judgment either way, but just to say that this is how things literally were taught, not in the field, no, actually from the book. So there you have it. It's actually a great book, though. So we don't recommend that you do this anymore. Probably not the best. Probably not the best practice. All right, so let's talk about the cartoon in our heads, because I think in terms of electrical diagnosis, this is something I guess I probably wasn't born with it, but a lot of people who are really good at diagnosing electrical circuits, electrical problems, have a mindset of like imagining things in their mind that may not actually represent reality perfectly, but give a good enough picture that they can sort of, I don't know how to explain. My brother and I just call it the cartoon in our heads. And so this image here of volts, amps, and ohms is one of the most common that's taught, and it's a good one. I mean, this is a kind of a modern version of this. Volts are the pressure, ohms are the resistance, and then amperage is the actual current that flows. And so when you increase resistance, you decrease current. It's actually an interesting thing, because one of my favorite questions to ask people is that what happens to your amperage when resistance goes up? And they'll often answer that your amperage goes up. And they're thinking in terms of electric motors. So you say, if your resistance goes up in the motor windings, does the amperage go up or down? And they'll often say up. Well, of course, that's wrong. When your resistance, when the ohms increase, then Mr. Amp here doesn't get pushed through the circuit as easily. But why do people think that? They think it because when you think of an electric motor, when there's greater resistance to the shaft moving, so if you have greater force against a blower wheel, if a compressor's, having a hard time running because maybe it's got bearing wear or it's running against, running high compression ratio, something like that, then we run higher amperage. And so we think resistance equals higher amperage, but that's not actually true in the windings. When a motor gets bound up, so when it can't turn, the resistance in the windings actually is less. And that's because of something called inductive reactance. As a motor runs up to near synchronous speed, the actual frequency of the electricity that's entering the motor, as it gets closer to that synchronous speed, there's actually a type of resistance that's generated as part of back EMF, and that's called inductive reactance. And that inductive reactance acts as a type of resistance against the current. And so it is the same thing as this cartoon, but this cartoon in your head helps get your mind straight. And so there's a lot of cartoons in our heads, and I'm curious, what are some of your cartoons? Are there any that you go back to time and time again? And so I'll give you some others. So this is another one that I've used a lot. There's different versions of this. This was actually an illustration that I had made for a lot of these. In fact, most of these illustrations that you'll see that we're going to go through today are illustrations that I had commissioned for the book that I took down to Haiti to help teach young people about electricity in order so they could do a little bit with solar, which was a lot of fun, by the way. Haiti's a tough place right now, but this is one of those. And so when you think of, high voltage goes to low voltage, that's one of the basic rules that I always talk about. But this water tower metaphor kind of helps you visualize that difference. High voltage going to low voltage, current being the water flowing out of the water tower, the actual work being done on the water wheel being the wattage, and then, of course, voltage being the potential difference. And in this case, we're representing it by gravity. So it's just a metaphor. It's not perfect. You can pick it apart. There's a lot of things about it that are incorrect, but it helps you get your head around voltage, amperage, resistance. In this case, we've got a little nozzle here on the water line that acts as the resistance, and then the work is actually what's being done against the water wheel, and that would be your wattage. And yes, my voice just broke up again, Caleb, so you can go ahead and comment on that. Again, getting these sort of metaphors in your brain really help with diagnosis. And I think a lot of technicians who struggle with electrical diagnosis, they don't have these cartoons in their head. They don't have these pictures that they can rely on. And this is just basics. I mean, this is just basic electrical science. But I think a lot of people, when you go to school, you spend a lot of time focusing on the math. So there's a lot about Ohm's law and how to actually calculate it. But the reality is that in the field, very rarely do we calculate anything electrically. It's really uncommon for us to calculate. And I'm not saying never do, because there are some cases where you do, but it's rare. Generally speaking, we're just taking measurements, right? And so what we do in school doesn't necessarily equate to what we do in the field, but understanding the relationships does equate. So understanding what happens when you change the amount of work you do, what does that do to the amperage? What does that do to the current? And then what does resistance do to current? And how does voltage affect current? Those are all things that do matter to us. And so the relationship matters much more than the math. And that's true with a lot of things. It's even true in refrigerant diagnosis a lot. So I like to always start with the relationships. If you do this, then that happens. And that's what we call a if this, then that equation or logic. If this happens, then that happens. And that's a good way to get started. And yes, I see all of your chats about how I need an air scrubber. Ha, ha, ha. Real funny. No, I am not sick. I just happen to control my indoor relative humidity to a very low level. And so my throat is a little dry, okay, which is why I've got my cranberry juice here. And by the way, even if I was sick, you can't catch a virus over a webinar, at least not that I'm aware. Caleb says I need a gym. You know what, Caleb? I've about had it with you. All right. These I stole out of that same old book. And I said the 30s, but I think it actually might have been the 20s. I think it's the late 20s. There's no vodka in my cranberry. My wife forbids spirits in the house now. So I am forbidden from any spirits in the house any longer. It's probably wise. So let's see here. These are actually illustrations that I had made out of that book. And these are really good ways of thinking about the difference between direct current, that's up here on the top, using a centrifugal pump driven by a pulley versus alternating current. And when we think about alternating current, a lot of people have really hard time getting their head around alternating current and how that works, because, which direction does it go? It goes both directions. But when we see this, we understand that the energy in this case is going to move this piston back and forth. So the water is going to alternate back and forth in pipe, whereas here it's going to circulate. But either way, we can accomplish the same amount of work. It's just going to be back and forth in this one, and it's going to be directional in this one. So once you get this picture in your head, it's a nice illustration to show one time. But once you get the cartoon in your head, you don't get it out of your head. And then now you always think of it that way. And so in terms of diagnostics and how that applies to electrical diagnostics and understanding electrical, I think it's really helpful to teach these things in this way, so that way you can get that cartoon locked in your head. Not everybody is visual, and I get that. In fact, I'm actually probably less visual than some people, but most technicians are visual. Most technicians, when you say you're a hands-on learner, when you're thinking about something that's happened in the past, you're actually accessing the visual parts of your mind. And so having these sorts of cartoons in your head can really help with that. Next thing, this is another example. Now we're equating water transmission, so moving water through pipes, to electrical transmission and conversion, generation, transmission, conversion in both cases. So when we look at a simple water system, we've got a steam engine that drives a pump. It's generating the energy on one side, and then it transmits it through the pipes, and then it's converted on the other end to a water engine, basically a water motor. So we've got an impeller here, and it drives it on the other side. Well, that's exactly the same thing that's happening here. Now we have a steam engine, and it's driving a generator. So it's creating this rotational electrical field that creates an alternating current that then transmits over a distance, over copper wires, and then is converted via a motor. So the opposite, generator and motor, pump and motor. They're both really the same thing. And so it helps you visualize that transmission and conversion side of things as well, that sometimes can be hard for technicians to understand, or newbies, I should say, to understand. Even technicians, though. So again, at this point, we're really this is all theory stuff. This isn't really diagnostics, but having this helps you quite a bit. Here's another one. How about high frequency versus low frequency? Another cartoon in the head. Imagining grabbing a jump rope and just bouncing it up and down. It doesn't have to be a jump rope. Could just be a regular rope. Could be a hose. Doesn't matter. Two people. And the faster you go, the shorter the wavelength becomes. The slower you go, the longer the wavelength. So we call this high frequency. Just means how frequently are you shaking it up and down, versus low frequency, you're doing it less often. And in the case of what we do day in and day out with electrical, that's just the frequency that the motor is turning, or the generator is turning, or the power generation at the actual power company, the power plant. That's where your frequency starts, that's actually the rotational speed of the generators, or the distance between the poles in the generators more specifically. But it gives you kind of a picture of what that is like, because we experience a lot of these things in regular life, and it just helps you get your head around it. All right, here we go. Anybody have any analogies that they like? Anything that pops in mind? Because I have a feeling that I'm just going to sit here and talk to myself for a while. So you can always raise your hand. So Terry Miller just raised his hand. So I allowed Terry to talk. And now if he unmutes himself, we can actually talk to each other. So far I have 4 people who are prepared to talk to me, but they haven't unmuted themselves and actually spoken to me. That's how that works, though. So if you want to talk to me, that's how you do it. Open or closed. I like the analogy of the drawbridge for open or close, because this is where water, and I've talked about this a lot, but this is where the water analogy breaks down. Because when we think of open and close in a faucet, when you open the faucet, water flows, and when you close the faucet, it shuts off. Well, that's opposite of how it works with electricity, which is why I prefer the drawbridge. The drawbridge, when it's closed, it's a path that the cars can go over. I often use cars as metaphors for electrons or current as well. When it's open, the cars can't move. But when we think of open and close, those concepts, open and close, there's a lot of analogies outside of electrical. So you have yes or no. That's a Boolean equation where the answer is either yes or no. In electronics, it's 1 or 0. Open or close, yes or no, 1 or 0. Those are all the same concepts. There's only 2 options, open or close. Joseph Davenport says, I'm listening. Wish I could see the PowerPoint. I've tried every setting there is, both here and on the website. Yeah, sorry, Joseph. I don't know what it looks like on your end. Maybe somebody who has actually gotten it to work can suggest that to you. But when you're thinking about things like relays or switches or contacts, all of that, you could just as easily say yes or no. So you could say contactor is closed, that would be yes. Contactor is open, that would be no. Contactor is closed, that could be 1. Contactor is open, that could be 0. Doesn't matter. So just a couple different ways to think about that. And yes, I am touching my face. I know that's not allowed, but I'm at home, so I'm allowed to touch my face at home. You know, those are the rules. Another couple of terms that are really important to understand. Short or open. When I teach classes, I always use the example, of your grandma's television. When your grandma's television stops working, or her stereo stops working, she says it's shorted. My television is shorted. And all that means is she's not actually saying that it's actually shorted, that there's a low resistance undesigned path. She's saying that it's doing something that she doesn't expect. And so people have come to call short circuits anything that's doing something they don't expect. But a short circuit is actually a very specific problem in electrical diagnosis. And it is an undesigned low resistance path. And it can be an undesigned low resistance path in between switch legs. This is one that's this is disputed territory, but I just use the common terms in our industry. So a good example would be if I have a short in between this yellow wire coming from my thermostat, which is the control circuit that powers my contactor. This is a very simple one. But imagine that this yellow wire was shorted to the white wire. What would happen? If the yellow wire was shorted to the white wire, it would also energize whatever the white wire was hooked to. So that could be the furnace, that could be electric heat strips in the case of a heat pump. And so we would call that a short. Now, Kevin says, wouldn't that be a shunt, not a short? And that may be a better way of saying that. Either way, it's a connection. It's an undesigned connection. I've heard it called a short quite often. Caleb says it's a short. I don't know. It's just what I've always called it. So I always just sort of say it's an undesigned low resistance path. So when you have a path between two things that aren't designed to have a path between them, to me, that's a short. Now, an overcurrent that's associated with a short, that's what blows your fuse. And so that's what we show here. And in this case, why does the fuse blow? The fuse blows very simply because we have this, we have our transformer here. Transformer goes into our fuse, out of our fuse to R, out of there to Y, and then it shorts to the other side of the transformer. So it's the same as connecting this to this. And we understand this intuitively because if you connect a battery, you connect the positive and negative side of a battery together, it shorts the battery out, right? You're connecting from one side to the other. You have unrestricted flow of current. Now, in the case of a battery, this is actually where it gets interesting with batteries. And I had to learn some of this doing more solar. With a battery, you have a limited power supply. So when you short out a battery, the battery goes dead, right? You ruin the battery. When you short out something like a transformer or the high voltage into your house, you have a much greater power supply because ultimately it's connected to all the way back to the power plant. And so in order to get it to shut off before it just just melts everything all the way back, you have to have these overloads. You have to have these fusible links. You have to have these circuit breakers that break the circuit so that way it doesn't damage the wiring. And that's in this case what our fuse does. Our fuse is on the secondary of our transformer. This transformer apparently has no primary because I just left that out for the sake of simplicity. When we have this undesigned low resistance path, that's what causes the fuse to blow. These are all basic. But what I find is that people who struggle with electrical diagnosis struggle with these basic concepts. If you drill back enough, generally speaking, they don't have a solid picture in their head about the basics. Because once you build those building blocks, then all you need is repetition. I get people who ask me all the time, hey, I need more experience. I need to be taught how to read schematics and diagrams. So let me see here. Eric says, just try the phone app and the slides are showing up. The slides might not work in a browser on a phone. Yeah, that might be what it is. But by the way, all of these diagrams, everything that you're seeing here, because I'm getting a lot of requests for the diagrams, all of them I have posted at one time or another on Instagram. I don't currently have them all at one place. And the reason is because I don't have my watermark on them. So if you want to find them one at a time, you can find them by going to Instagram and just looking back through the history, and you can find them all. Feel free to steal them from there. But I don't want to create a single file repository of everything that I've created, because then next thing I know, it'll show up in a book somewhere. Not that I mind people using it, but you know how that goes. The point of what I'm saying here is that when you drill back far enough, usually it's a misunderstanding of fundamentals that causes people to get stuck, or they learn the fundamentals and then they just don't do enough reps. Because frankly, any of us who are pretty good at reading schematics, and I don't claim to be, honestly, we think of guys who do a lot of commercial work and do it every day in and day out. They tend to be the ones who are good at reading schematics. Why? Because in order to do commercial work on large, complicated equipment, you have to get a lot of reps in reading schematics. And so they understand the fundamentals, and then they get a lot of repetition, and that's how you get good. Francisco says, Bryan, I have a question regarding fuses. I have a 30 amp fuse at 500 volts on a 3-phase compressor. I've asked several people and still don't know if anything above 500 volts will also blow fuse, or only over amp situation. I normally see 600 volt rated fuses. It's fine to use a voltage rating on a fuse, on a fusible link, that is higher than the rating of the old one. So it's totally fine to use a higher rating on the voltage, not on the current. So you got to match the current exactly, but it's fine to use a higher voltage rating, because that's just saying that is the voltage at which, when you go over that, it can actually bridge the fuse itself. So a higher voltage rating on a fuse is a better quality. It's not actually there to protect the unit for that higher voltage. Wiring diagrams are really big. Let's talk about opens now. So a lot of people will say that a short and an open, they'll call an open a short most commonly. That's most commonly what will happen, because they start calling everything a short. But an open is a specific type of fault, and that is where there is no path. So a short is an undesigned path, generally a low resistance path that results in a overcurrent condition that blows a fuse, trips a breaker, something like that. An open circuit is a break in the path of some sort, so an undesigned break that results in things not happening that should be happening. And I used to always teach it this way, and I realize I confuse people more, but I'll go ahead and confuse you. I used to say, when you have a short, something happens that should not be happening, namely blown fuse or some component being energized when it shouldn't be. When you have an open, there's something not happening that should be happening. And the tricky part is that a lot of times short circuits cause opens. A good example would be that this is a short circuit, but once it blows the fuse, now this is an open. So the short circuit causes an open. And the same thing is true of a circuit breaker, right? When you have a shorted compressor, the short causes the breaker to open in order to protect the wires. To answer the question, there's some questions in chat about fuse types. Yeah, you have to match the fuse type. I'm not saying that you can just swap in a different type of fuse, because you do have different times. You have slow versus fast. You have different amperages. So I'm not telling you to swap it out with a different fuse in any significant way. But the actual voltage rating on a fuse, that is a rating that has to do with the point at which an arc can go across it. So you can use a higher voltage. And he's asking me how much higher. Again, most cases, they're going to be very close, because they're going to be the same general design. So it's going to be rare that you're all of a sudden going to have some fuse that looks exactly like another fuse that's going to fit, that's going to be a significantly different voltage. Let's talk about schematics. So one thing that's interesting is that when we get used to looking at ladder schematics, after a while, we get used to diagnosing left to right. And we start to think about electrical circuits in terms of left to right. That's kind of a mistake. And it's something that happens actually with more experienced tech sometimes, because this is an alternating current circuit. So we have L1 here, we have L2 here, and then everything connects in between. And in terms of isolating circuitry, that's helpful. Now, this is kind of a modern ladder schematic or ladder diagram where not everything is even left to right the way it used to be. I mean, a traditional one, you would have two lines and everything would connect in between. And a lot of manufacturers, especially on the residential side, are starting to go away from that. But it is helpful when you first get started to start on the left and work your way to the right. But the reality is it's alternating current. So it's not like the electrons are moving from one side and just going to the other side. And here's where this gets interesting. So let's talk about on this schematic here, you have a what they call what do they call this? Analog, the right terminal. That's not the right term. My mouth is running much faster than my brain at the moment. So they call this like a 1+ contactor. And so you have your one set of contacts here, and then you have the shunt, which is just connected across. And that's why they say, thank you to everybody who's saying that. So that's why it says 23 and 23, because electrically, these are the same points, which means that if you have this sort of system, you have L2 connected all the time. So L2 is connected all the time, which means that there is potential present everywhere in the circuit at all times, even when the system is off. But which side is that coming from? It's not coming from this side. It's not coming from left to right, because if we think just in terms of left to right, well, there, we got an open contact right there. No, it's coming from right to left, because this is the other side of the circuit. This is a really interesting one anyway, but this is what happens, is that a lot of technicians, they'll take a voltmeter and they'll look to see if voltage is present, and they will measure L1 and they'll measure L2, and what they'll find is, or they'll measure somewhere in the circuit, and they'll find 120 volts to ground on both sides, and they'll think that there's, in most cases, they're gonna have a misdiagnosis, because they're imagining that it's coming from this side, when in reality it's just coming from the other side. Another interesting thing about this particular diagram, which is why I use it, because it's a kind of a weird one, is we also show here, we have a crankcase heater, and we have our crankcase heater switch, and so it goes through here, through the crankcase heater and back here, which is interesting, because how would that work? Because it's both connected on the same side, right? How would this ever energize? I'll wait until somebody explains it in chat, or somebody who wants to raise their hand. How on earth would this crankcase heater ever energize given the way that this is wired? Doug says it's a carrier. That's true. So they use magic. So the answer is, Jason says it's only energized when it's off. So it's only when the contactor's open. Well, how does that work? It works because when this switch is closed, this is a good way, because I like to talk about a voltmeter as a voltage drop measurement tool. It's a way to think about a voltmeter that's helped me a lot as I've gotten more and more comfortable with a voltmeter through my career. When this contact is closed, if I take a voltmeter and I connect one half of the voltmeter to 11, and I hook the other half of my voltmeter, the other side of my voltmeter, to 21, if it's closed, what am I going to measure? I'm going to measure 0 volts or thereabouts. Why? Because a voltmeter is a voltage drop measurement tool. I'm not measuring a potential difference between the two, because when there's a closed switch, there's very little resistance in between these 2 points, so therefore there's almost no voltage drop, right? Now, if I open this switch, now what is the voltage drop between these 2 points? Well, now it's significant, right? Because I have an air gap in between. So I've got potential here, I've got potential here, there's an air gap in between. That voltage drop is the entire voltage, right? Because now that resistance in this air gap is significant. It represents the entire voltage. And so now I have 240 volts present across here. Well, that's what this crankcase heater uses, because now it acts as the path to get in between the two sides. So in actuality, what's going to happen in this circuit when this contact is open, and this is obviously still closed because that's just a shunt, what's going to happen is we're going to have, and again, I'm drawing it this left to right way, which is, it's just silly, but because it's not DC, it's going both directions. But it's going to come through here. It's going to go through the switch. It's going to come through here, and then it's going to travel through the compressor. It's going to go through the contactor and then back the other side. So this run winding is going to take the brunt of that. Now, why doesn't the compressor start running? Why doesn't it overheat? Well, it's because this crankcase heater has a significant resistance. And so the answer is this run winding is actually going to warm up, and that becomes part of the crankcase heater strategy. It's not enough current for it to run the compressor, but it is enough to have a warm run winding, because if you've ever measured the resistance on a compressor winding to winding, and this is one of my biggest pet peeves I see people do, is they will measure. I'm going to allow Tim DeStasio to talk if he wants to. So, Tim, I'm allowing you to talk. If you want to unmute yourself, feel free to join me.
Hey, Bryan.
Hey, there you are. You're the first guy to join me on this podcast. I'm so happy. I thought I was going to have to talk the whole time. How's things?
Good, man. How are you?
Very good.
What did you want to know?
I wanted to know something that you wanted to talk about related to electrical.
Oh, I was actually going to answer your question that you just answered. The power goes through the windings of the compressor because the windings just turn into a conductor at that point. You're not creating an inductive field.
And so your winding, in this case, your run, well, it's actually all of them, but your run winding in this case, in the way that I just showed it, it's acting as a resistive load. So it's essentially just a heater. Do you have a good way of thinking of that? Like, how do you describe these things? If somebody, I'll ask it this way. So somebody says to you, hey, I have a really hard time reading schematics, because I get that a lot. How do you answer that question? What do you say to somebody? Tim muted himself again. Fine. Fair enough.
I thought that was a public question. I was allowing others to.
Okay. Well, that's fair enough. Others can also add in, but what are your thoughts?
I mean, I think it's pretty much how you explained it, that current flows in, everyone thinks that current takes the path of least resistance. And what we have to remember is that it takes all paths. And so it just depends on how easy that path is, and you'll have the most energy or the most work that's done. So if that easy path is a short circuit, a bare wire to wire short, then you're going to get a lot of energy. If it's not a very good path and you've got a lot of voltage drop across it, then you're not going to get a lot of energy at one place. But all those concepts, like you said, are just important to kind of instill early on, and then get them out there working on it to actually have them read those readings as soon as possible. But they got to have what you're doing here.
Well, there you go. And I agree completely, because you agreed with me first, so then I agreed with you. This has been just lovely. But yeah, what you pointed out was really smart about the parallel paths, that this idea of paths of least resistance, because this wasn't in my slide and I wanted to mention this. When people say electricity takes the path of least resistance, no, it takes all paths of sufficiently low resistance. That's one caveat that I will add, because does electricity take all paths? Well, no, because an air gap is technically a path that could be bridged, but isn't, because the resistance is sufficiently high that no electrons actually move through that path. But when we're talking about things like electrical circuits, if there is a path, then electrons are going to move across that path. They're going to move across it proportional to the resistance in that circuit. So you look at resistance, you look at voltage, that's going to tell you how much current is going to move across that path. So left to right, you sell yourself short when you do that, when you only think in terms of left to right, because in a 240 volt circuit, it's also coming from right to left. So another thing is that when you have run winding, for example, here, and you have the crankcase heater, the reason why the run winding doesn't really get that hot is because your windings in your compressor are actually pretty low resistance. And I've had this happen a bunch of times. So I've mentioned this on several podcasts. So forgive me if I've already said this so many times. When you measure across from leg to leg on a compressor, so say you measure from run to start and then start to common, run to common, those are going to be very low resistances. In some cases, those resistances will be so low that your meter will actually ring when you're measuring leg to leg. And that doesn't mean that your compressor is always going to draw these ridiculously high currents. Because if you work Ohm's law, it will look like you're going to have these, 100 amps, whatever. That's only what it draws when it starts. Once that compressor gets moving and you get that inductive reactance, that's additional impedance is what we call it. It's additional resistance, electrical resistance that shows up once that motor starts running, once that inductance kicks in. And so the problem is, this is where rubber meets the road. A lot of technicians, they will measure from leg to leg and they will see these very low resistances and they will think that it's failed, especially if they use something like one of those megometer things and they connect leg to leg. That's a misunderstanding of how those things are supposed to work. Those are always to go to ground. And so when you're checking from for shorts, you're generally checking to ground. Now, we had this happen the other day with a very smart technician who works for us. We had a situation where he was using a meter, very good quality meter, and he measured from leg to leg, and he checked the Copeland specs, and he saw that it was measuring lower than what the Copeland spec said, so then he said it was failed. The problem is that a lot of meters, even pretty good quality ones, when they get below an ohm or in that range, they get kind of inaccurate because it's such a small measurement. And so he was seeing a lower measurement than what Copeland said, but it was just his meter. His meter was just showing a lower ohm reading than what the manufacturer spec said, and so he condemned the compressor. The compressor was not bad. So leg-to-leg shorts are something you got to be really careful with diagnosing, because you have to understand your meter, you have to look at the specs from the manufacturer. generally speaking, we're going to find short circuits by measuring to ground, not by measuring from leg to leg. And frankly, I always use what we call the redneck test. And the redneck test is that once you get done confirming that you think it's the compressor that's shorted, we'll then isolate the compressor, start it back up, and see if everything else runs without the compressor connect. And that gives you an indication. We don't condemn compressors in almost any application because they say that they're bad on a meter if they're not actually drawing overcurrent in real life. So again, yeah, Bert did a video on that. That's a good example of that. Michael says, unplug it, ? Yeah, so disconnect the compressor. If it's a plug, well, it's just a plug, just disconnect it. If it's, terminals, take a picture of it so you know how they go back on, take the wires off. I don't take them off at the contactor. Michael says, take them off at the contactor. No, I take them off at the compressor. I take them off at the compressor, I tape them up, and then I put everything back together and I start it back up. And if everything else runs, and it was before it was shorted out, it was tripping a breaker, and now everything else runs, well, now I've isolated the problem down to the compressor, which this is the number one way that good diagnosticians diagnose is they do isolation and confirmation versus just using a meter saying, hey, it's bad, and then moving on. You always have to confirm at the actual device, isolate. And if possible, use other parts to replace to even check and make sure, to double check. This is where when people work on big facilities, this is how they do it. They're not being parts changers by just verifying, checking against checking, making sure that it is that part before you condemn something and say that it's bad and throw it in the trash, right? To always double checking. And this is where even I use jumper wires more often than I even use meters in a lot of cases. It's very difficult for me to give a lot of examples of this because it happens in real life so often. The situations vary so much that you run into.
So you touched on something and it kind of got me thinking. So on this diagram, you've got a single pole contactor. I've seen technicians, they find a bad contactor and they replace it and say, well, I don't have a single pole contactor. I've got two pole contactor. And that's always better than a single pole contactor. I'll throw it on there. Well, in this case, if they do that, their crankcase heater will never energize. Am I correct?
Correct. Yes. If you do it that way, your crankcase heater will never energize. And really the only right way in this application is to use either the same sort of contactor or to shunt out one leg of your contactor. So you can take one leg of your contactor and just connect from top to bottom with a big piece of wire, and that will essentially shunt that leg out. But again, sometimes that requires double lugging or whatever. So in these cases, this is the one rare case where there isn't another way around that. For example, Train had a version of this, but it wasn't the same sort of situation where they would just connect to the bottom side, but it wasn't feeding through the compressor winding. I would have to test it. I don't know for a fact, but if you took this and if instead of connecting it in this way, if I just hooked it from here and then over to the other side so that way it would be energized. Actually, no, that wouldn't work. I'm trying to think here. Yeah, no, the only right way to do this would be by shunting out one side. That's really the only way. And again, I don't even know if I want to tell somebody to do it that way in this case.
Yeah, that's a lesson to text that you may be going back behind another technician. You may be putting on the fourth contactor in the lifespan of that unit. It might be a good idea just to check the wiring diagram and make sure that you're putting on the right style of contactor before you just put on what was already there.
Yep, absolutely. And this is actually something we've talked about a lot in the past when those were more common, because that's not actually stock on most units even that come with that wiring diagram. That's sort of a generic wiring diagram, and they have a little star that this may exist. You don't see that in the field as often as you once did, and so it's not as big of a deal, but there was a time when that was actually quite common. That is an issue, and you have to pay attention to those details. All right, so voltage drop measurement tool. I'm going to read this line because it's a confusing line, but once you get your head around it, I think you'll find it really helps you be a better diagnostician. Think of your voltmeter as a voltage drop measurement tool. Okay, we've talked about that before, but here's the line. The voltage drops across each resistance or load, whether designed or undesigned, in the circuit is proportional to the percentage of the total circuit resistance that load represents. I'm going to tell you a story to help you get your head around this particular phrase here, rather than, because I could draw it on a circuit and start throwing numbers at you, but if I throw numbers at you, a lot of techs check out because we don't think in terms of numbers. If you look in the book's going to show you different ohm ratings for different loads, and that's how they teach it. But think of it this way. Okay, so I've got a circuit, and it's not working right? And I find that I have a bunch of resistance in a loose lug in a disconnect. There's a loose lug in a disconnect, and so it's carboned up, it's been arcing, and so now there's additional resistance in that loose lug, right? We get our heads around that. There's additional resistance. Am I going to measure a voltage drop across that? Well, yeah, I will. Now, it might not be significant, but if I measure a voltage drop across that, whatever voltage drop I measure is proportional to the percentage of the total circuit resistance that load represents. So let's take this really simple. If I have an arced up terminal and I measure 24 volts of drop across that arced up terminal on a 240 volt circuit, what does that tell me? That tells me that 10% of the total circuit resistance is in that terminal. Let's make it even more simple. Like we said before, if I go back here and I measure 240 volts from here to here, from terminal 23 to terminal 11, I measure 240 volts. That tells me that 100% of the voltage drop in this circuit right now is present between those 2 points. And that makes sense. That's why you measure nearly the fully applied voltage across a load, right? If I measure between common and run, right? Measure between common and run, and this contactor is closed. What am I going to measure? Going to measure 240 volts or thereabouts. If 240 volts is present from here to here, I should measure about 240 volts from here to here. Why? Because nearly 100% of the total circuit resistance that exists from here to here is present from here to here. If this had 10% voltage drop in it, then it would also have 10% of the circuit resistance and vice versa. I'm interested to see if that makes sense to anybody. Is there anybody who's like that? They don't get that at all. Let's see if I have any hands raised. So I've got a couple hands raised. I'm gonna allow. We got Chris Roseberry, we got Michael Makara, we got Freon Man. Any of you want to comment on that? You just unmute yourselves. Jamie says no, use numbers. Well, I did use numbers, and it still didn't make sense. So normally how they would show it is they would show multiple loads in series, and so they would teach this as a series circuit. The thing is that most circuits we work on aren't series. Let's see. So somebody's talking. Who's here?
Me?
Hey, Freon Man, what's going on?
How are you, Bryan?
Very good, very good. Who is this?
I'm Jim Landry, and I own Reliable Refrigeration in Boston.
Sweet. Are you on lockdown right now?
We're not on lockdown, but they did suspend permits on 3 of my jobs this week.
Is that good or bad? Does suspend permits mean you get to work without them checking up on you? Because that sounds good.
No. They you can't work at all.
Oh, okay. Well, that's the wrong direction. That sucks.
Yeah, that is the wrong direction. Absolutely.
So what are your thoughts?
I only listened to part of it because I was trying to figure out why I couldn't talk most of the time. So I apologize.
Okay, no problem.
This is my first time I've ever actually went to a live webinar.
All right, sweet.
So I got your email a while back, and I signed in, and I downloaded Zoom, and here I am.
There you are. Good deal.
I follow. I look at your thing every day at night and all that.
You look at my thing every day at night. That sounds iffy.
Yeah. You're you know what I'm talking about.
Tech tips. Yeah, I'm with you.
Yes, sir. Yeah.
All right. Well, thanks for being here.
All right. No problem.
All right. Who else we got here? Chris?
Yeah. How you doing?
Good. What's going on with you?
I just want to share a story of a unit I had the other day.
All right. Let's hear it.
Fan wouldn't start. The compressor was humming. Looked at the capacitor. Fan side is bad, right? So tell the homeowner, hey, capacitor is bad. I hook it up. The breaker was tripped. Reset the breaker. Went outside. Pushed the disconnect in. And breaker tripped again. So, of course, most of the time it's a compressor issue. Unplug the plug, go back in, reset the breaker, come back out, it tripped again. And long story short, the fan was actually shorting out, the whole unit and tripping that breaker, which was a first for me because most of the time the fan doesn't, have enough to trip that. But
yeah, it is more uncommon on residential equipment to find condenser fans shorted to ground. And do you know why that is?
I like I said, I took everything out, thought it maybe been the contactor, took all the wires off, and I don't know why that happened. Like I said, that was my first interaction in 15 years.
Any motor can theoretically short out, but condenser fan motors are much less likely to for a couple reasons. One, the forces at play aren't as great, and so you don't have as much torque going on. But secondly, because the gap in a condenser fan motor is air. In a compressor, you have that whole thing is full of refrigerant, and you have oil, and you have everything else. So when you have a some sort of catastrophic issue in there where something breaks off and goes flying around and banging around, it's much more likely to cause a consistent to ground short than it is in a condenser fan motor. So there's a couple different reasons, but yeah, you'll definitely find condenser fans cause shorts more in larger commercial applications where you have greater forces at play and that sort of thing. But on residential, it is a little bit more rare, but good find. And that's isolation diagnosis. What you did there was isolating and kind of walking down the line until you figured out which component it was, which is in my book, a totally acceptable way of doing it.
Awesome.
All right, brother. Thanks for joining me.
Yes, sir.
I'm not going to spend a lot of time on this particular phrase, the voltage drop measurement tool. Either you get it or you don't here, and I'm not doing a very good job of describing it, because every time I describe this one, it's hard for people to get their head around. But I guess to sum it up, we mostly work on parallel circuits, and so that means that you have only one load in the path between the two sides of your circuit. So in the case of a 240 volt circuit, that would be between L1 and L2. In the case of 120 volts, that would be between L1 and neutral. In the case of 24, that would be between hot and common, right? And so each one of those circuits, parallel paths, only has one load. And so when we measure across the load, we're measuring generally 100% of the voltage drop, because or nearly, because almost all the resistance is going to be in the load. In the case of, let's use an example, compressor, that'd be the compressor windings. In a contactor on the Y circuit, that would be the contactor coil, right? So you'd measure 27 volts or whatever it is across the contactor coil. But if you add another voltage drop in parallel or in series with that parallel load on that same path, then that voltage drop, depending on what percentage of the resistance is, that's going to be what percentage of the voltage drop it is. And so this is how we can use our meters to find things that are undesigned, poor connectivity, whatever, and we can use our meters to find problems in the circuit. And it's also helpful when you're diagnosing, really complicated circuits, and you put your meter on it and you measure some weird voltage. What are you measuring? You're measuring the voltage drop between those 2 points. You can say potential difference, that's fine, but a meter is always 2 leads, and you're measuring between 2 points if you're using a voltmeter. Next thing is, I always want people to look for the obvious. I can't tell you how many times, and I use this is another image that I made for the folks in Haiti. How many times it's just the simple things that people do wrong, where they wrap it the wrong direction, around a terminal, or they use they take a stranded wire and they wrap that around the terminal, and then the stranded wire is coming off all over the place rather than using a crimp-on terminal, or they make a crimp-on terminal incorrectly, or they leave a bunch of bare wire exposed, or you have wires that are crossing one another, or crossing a discharge line or rubbing out on a piece of metal. There's a lot of different things that are just obvious diagnostic no-nos that an experienced technician keeps their eyes open for, that a newer technician often will miss. And from a diagnostic skill standpoint, that is a really invaluable skill. And also, just never allowing these little details to just pass by the wayside. Double lugging is a really big one, where people take multiple wires and jam it underneath a lug where you're not getting good connection. And so all of those things can add resistance to the circuit, which can then cause problems because it causes voltage drop. Additional resistance causes voltage drop, which is part of what I was describing there. It's the same thing when you have a switch that starts to get carboned up, like a contactor, that can add voltage drop to the circuit and cause problems. Kevin says, so far no air quotes, but we got to rub out. Yes, that's true. I always do air quotes, but see now if I do air quotes, you can see me, and so that kind of ruins it. And I do talk a lot about rub outs, and it's not a dirty thing. It's just what happens when a wire rubs out on a metal part, and when they love each other very much, they create other little wires. Breakers, overloads, and wires. This is we're gonna finish up here on one of my favorite things that now you're crossing the line over there in chat now. Breakers, overloads, and wires. Wire sizing is super important. It really is very important, but it's really misunderstood in all segments of the industry. So not just by air conditioning and refrigeration technicians, but also by electricians. Because wire sizing is not as simple as this chart right here. So this chart here shows 14 gauge is 14 amps, 12 gauge is 20 amps, 10 gauge is 30 amps. These are all based on sort of worst case scenario applications using, I think it's, 60 degrees Celsius wire, which is what NM is. NM means non-metallic. That's what we call Romex, trade name Romex, right? And so when we're used to working in residences and they have that 60 degrees Celsius insulation on them, or it's Romex, this is where these sizes come from. But also this is copper. This isn't aluminum. So there's a lot of different variables that factor in here. And there's also some derating variables, meaning there's some cases where if you're running through very hot areas, then you have to derate for that. Lots of different factors. But the one thing that's sort of a saving grace for us in our industry is that the manufacturers give us on the data plate what we size the breaker to and what we size the wire to, believe it or not. And if you follow that as an air conditioning contractor, you're safe. You've followed proper practices. And so let's use an example here. This is actually a pool heater. Now I know I'm good. I know I'm going to do this, and everybody's like, because this is one of these like really disputed things out there in the industry. But trust me, do your research. You will find that this is the case. Minimum circuit ampacity, amperage capacity of the wire. This is what you size your wire to. So you find a wire that the NEC says, and there's a lot of factors. Okay, so I'm not going to give you all these factors, but if the NEC says that it can carry 40.21 amps under the conditions that you're in, wire length isn't one of of them, by the way. That's one people will always say, is that the length of the wire is voltage drop. That's actually not one of the factors that the NEC requires you to consider. Won't go into why that is, but that's actually only a suggestion in the NEC. It mostly has to do with the type of wire it is, the insulation, whether or not the connections, what the connections are rated for, and what the temperature is, and how many wires are running through what they call a raceway. But anyway, you find, that was a lot. You find the wire that's appropriate for this size, and that's the wire you connect. And then you find the breaker. You can connect up to a 60 amp breaker. Now, you could go down to the size of the wire ampacity. You can go down. Now, you may have nuisance trips, but you cannot go above this. So you can put a 60 amp breaker on a wire that's designed to carry 40.21. And people will say that is complete heresy. You're going to burn down a house. No, you're not, because this appliance has an overload built into all of the motors that will shut them off before you have a consistent overload condition that could melt the wire. So the reason why they allow for it is, one, it's because of starting amps, because starting amps are higher and they don't want to have nuisance trips. So that's why they allow a bigger breaker on a wire that's smaller. Because again, on this, most people would say, well, you got to put a number 6 wire on it. No, you don't. You may have to based on other factors. But as far as we're concerned, as AC technicians, as long as the wire will handle 40 amps, we can put a 60 amp breaker on it. Tim says inspectors don't go by this, and arguing with inspectors like wrestling a pig. You wear yourself out, and after a while, you'll realize the pig likes it. Yes, and that's fine. I'm not telling you to get in fights with inspectors. Do what you've got to do in your area based on what we call the AHJ, the authority having jurisdiction. But most inspectors I found, because I went toe-to-toe with an inspector on this politely. I sent them the Michael Holt video. I sent them my article I did for the news, and I said, just take a look at this, and they changed their mind. Yeah, you'll find some people who want to fight, but if they do, then just do what you got to do. This is another example. So here's a carrier. This is actually my house. We have a 50 amp breaker, and that's what I've got in my panel. And in this particular case, a number 10 wire is actually acceptable given the type of wire and the insulation rating on the wire that's being used and all that other stuff. So on my house, I've got a 50 amp breaker and a number 10 wire running to my condenser. Hopefully you don't hear the fire trucks from your house when my house burns down. No, the point is that this is allowable. Based on the National Electrical Code, Section 440 of the NEC. And the reason why I bring this up is just because it's a fun one. It's one of my favorite topics, because this really has very little to do with diagnosis. It's more just about the electrical code. That is that. See, look, there's the end of the slideshow. But the biggest thing that I wanted to kind of point out was, from an electrical diagnosis standpoint, is I think a lot of people who really struggle with electrical diagnosis struggle with having the cartoons in their head, having the pictures, having those real basics. And it's not, I think a lot of people would argue that it's math. I don't think it's math. I know a lot of really good diagnosticians who are terrible at math. I'm not good at math. I don't use math in electrical almost ever. I guess there's a few cases where I do, but very rarely do I use math with electrical. More what I do is I understand the relationships between concepts, and I have a visual in my head of how things work. And then once you have that basic visual, then you get to schematics and ladder schematics and diagrams, and then you just have to use them a lot. So you have to get a lot of repetitions on it. And that's something I'd like to see schools doing more of, and apprenticeship programs doing more of, is giving people a lot more repetitions on schematics and diagrams. And some of it can be that you draw them yourselves. Some of it can be that you're diagnosing based on them, but you have to be using them in conjunction with a real piece of equipment. You can't be just going through schematics. I think you do yourself a disservice, because you have to have a reference to a real piece of equipment. And so for those of you who still find yourself really struggling, take a scrap piece of equipment out in the scrapyard and just go through it, rewire it based on the diagram, do it again, grab another piece of equipment, do the same thing, get some reps in of looking at the diagram and equating that to a real piece of equipment over and over. And I think that will help you quite a bit. Anything anybody wants to talk about before we wrap up? Because it's 9. We're pretty much done here. This was kind of weird. I don't like the PowerPoint presentation. I need to let you guys know how, because I wanted to talk to you all more than you did. Let's see. Eric Kaiser's here. I'm going to let Eric talk. I want Eric to tell me what I missed. So you got to unmute yourself, Eric, if you're still here.
What's up, Bryan?
Hey, man. How's things?
Good. How about you?
Very good. I think part of what made this difficult is that there's just so many darn people on here compared to how many I usually get.
There's a lot of people on here, and looks like you got good attendance tonight.
Yeah.
I'll say one of the biggest things that I see technicians struggling with in diagnosis is troubleshooting to ground, and trying to troubleshoot circuits to ground, and not taking the readings across components to be able to diagnose the component. And I think you went into it there with the measuring across the the contactor, and you should have the same voltage when you're looking at that ladder diagram between 11 and 23 and 11 and 21 when that contactor is
right. Exactly. Yeah. That's a really good example. And measuring to ground in general is just not the best practice. But just out of curiosity, what are some times that measuring to ground is a good practice?
Measuring to ground for me is a safety piece to just find out if there is voltage present before I go sticking my fingers in there, because I'm going to create, or the technician, whoever is going to go in there, is going to create that path to ground. So anything I'm going to touch, I want to know if there's power on it.
Absolutely. And that's a really good point. So Michael, I'm going to unmute you because Michael said he had a story.
Hello?
Hey, what's the story, Michael?
What's going on?
Hey, not much. Just sitting here talking to you. Good day.
I'm having fun up in Connecticut here.
Awesome. I was up in Connecticut recently.
Nice. So a couple weeks ago, I was working on this was a Lennox rooftop, and I will say Lennox has the most interesting diagrams of all the units. Mm-hmm. This particular unit was designed for medical space, but then they converted it into a pharmacy, and it had a 2-speed, 3-phase motor with dual contactors. So low speed would energize one contactor, one would drop out, energize the high-speed contactor. Air balancer went out and was trying to do an air balance, and when he ran the unit in cooling, it started short cycling. I got sent out there to go look at the problem, and so I started going through all the voltages, checking everything. It was on an automation system, so I took it off the automation system, and I checked low voltage, everything was good, checked high voltage, everything was good. I ran the unit standalone, and everything was fine, and when I put the automation system back online, it was short cycling. But I had no voltage drops. Everything was good on the primary and the secondary sides of the transformers. So long story short, I will say that I found that the current sensor on the rooftop unit was when the fan would drop out from low speed to high speed and the contactors would switch on a call for cooling, it would lose its control status, and the automation system would cause a short cycle, would energize 24, take it away, energize it, take it away.
Huh, interesting.
Yeah, we had a younger guy there, and he couldn't figure it out. So after a while, going back and forth, I had the automation company program a delay. But it was something that was interesting because most guys walked up to the unit and said, "Oh, fine, all the voltages are good," when the unit is running standalone. But when automations, and they always blamed it on the automation to a certain extent, but they didn't check all the voltages and see what was truly going on with the unit.
That's actually a really good point. This is the concept of always test under the conditions that are present when the problem exists. And this is the challenge with using test modes in a lot of cases. Any sort of overrides, if you're not testing, especially with weird problems, if you're not testing under the conditions under which the issue shows up, then you can miss things. And that's just a really good, a thorough diagnostician always runs all modes and operates the system under the conditions that it's going to actually operate under. So yeah, good catch there.
Yeah, and also just to go back earlier, I wanted to just let some guys know too, because I ran into this with other guys, like you said, with the your technician who was using the ohm meter. A lot of these flukes, field piece, whatever you may have, they have an auto range on their ohms, and sometimes it'll change the reading automatically on you. You can't always pick it yourself. So I always tell guys, be knowledgeable of whether it's reading K, mega ohms, where the decimal point is on the meter makes a huge difference.
That's a big one. And I see that all the time. It's like you expect it to auto range back and then it doesn't, and that throws you off. So that's really big. Well, thanks, Michael. I appreciate it.
All right. Thank you.
All right, Jason, what do you got?
Hey, I've got a little story here. Really kind of a simple story. Went out to a call the other day, and the guy's thermostat had blown up. It was a residential unit. I want to say it was a 4-ton mobile home, 2 years old. It blew up his thermostat, indoor board, and outdoor board. So we went in and got him new boards, new thermostat and everything. Got him put in, but before I went to figure out the problem, I didn't put that thermostat on the wall because I wasn't about to blow up another thermostat.
That's wise.
Made sure that the boards were fused out properly, and then I just jumped it at the thermostat into cool mode and heat mode to see what was going on there. Tried to jump it into cool mode, jumped red to orange, yellow, and green, and it blew the fuse just like that. So I went in and put my popper in there and figured out it was on my reversing valve wire. So I just went, figured out, the thermostat there. Then I went to the air handler, jumped it out there, and I figured out it was in the outdoor unit. So I went out there, undid the orange wire, then put all my power back on at the air handler, went back out there and just touched the wire to see if it would arc, a big arc, and it did. So this is where it kind of got interesting because I was like, it's a 2-year-old unit. I wasn't expecting anything major to really be wrong like this. But I went and unplugged the wires off the reversing valve coil, tested the resistance across that, and it was reading really low. But I went ahead, put the orange wire back together just to see if the short was in those wires. And that was something that another guy had showed me, just to the isolation technique like that. Always make sure it's not just a short in the wires going to that thing that's got the problem. And yeah, it was just that coil that was bad. Pulled that thing off. And the only thing I didn't have to isolate was I didn't have a solenoid magnet on the truck. Thankfully, the reversing valve was good, but I went and bought one that day also. Just a little tip there I thought I'd share.
Yeah, and that's a good one. And that's actually a weird one too, because it can actually be both ways. It's tricky because you can have a shorted solenoid, which is what you had. But the other thing that you got to be careful with is that solenoids do run low ohms by themselves, because it's that inductive reactance that shows up, because a solenoid is a magnet. I mean, that's really what it is. And in some cases, if you have, for example, this is a good example. If you pull a solenoid off of the reversing valve and you energize it, the thing will overamp and it will overheat, and it can actually fail that way. And so in some cases, when the valve isn't actually engaging the way it's supposed to, that can actually result in the solenoid coil drawing high amps. But you were correct in that when it happens instantaneously like that, when you have that high current right away like that, and it's actually taking it out, tripping the fuse right away or giving you the big spark, that's an indication that it's actually shorted within the solenoid. Because generally that condition, it's just like if you've ever had a contactor that gets stuck open where it can't engage into the magnet, that will result in high current, but it's not going to be that instantaneous kind of like really high. It'll actually, in a lot of cases, take out a transformer before it even takes out the fuse, and which is sort of it's a weird thing about the transformers we work on, because the transformers we use are 40 VA, which means that if you take 40 divided by 24, it means that they're rated for about 1.66 amps, but yet we put 5 amp fuses on them. So when you have cases where you've got a coil or something that's not engaging properly and it's drawing 3 amps or something like that, it's not going to blow the fuse in a lot of cases. It'll just take the transformer out on you. But anyway, so just a side note there. Yeah, that isolation diagnosis is the way to do that. There are purists who work in very high-end controls environments who will say, well, doing that isolation diagnosis creates this arcs and that can damage controls and all that. And there is areas of our industry where that's true, but especially in mostly what we work at, 24-volt controls, isolation diagnosis is absolutely the way to go. And it's the way that I've done it most of my career versus, pulling out an ohm meter and doing it one at a time, because there's the challenges that are associated with ohm meters that are 9-volt batteries.
Sure. Yep. Thank you.
Cool. Thanks, man. Sorry, poor Jason. I kind of went off on him there. I got to be careful before going full nerd on people. Got to prepare them. Anyway, well, thank you all for joining. I'm going to actually set, because the only thing I regret about this episode is I would have wanted to talk to more of you. And so I'll set some rules and guidelines next time for how to interact, and that'll make it a little easier. But we're going to get some more people on the live podcasts, other contributors, rather than just me yakking on. So hopefully you got something out of that. It was a little off the cuff, but we'll be doing more of these soon. And hey, thanks for listening, and we will talk to you next time on the HVAC School Podcast.